on a circle, we are going to talk about how they relate to the radius. And we will actually be using some of our triangle theorems, the Pythagorean theorem specifically, to help us relate these properties. So the first thing I want to do is read this definition at the top. So tangents, now not to be confused with the tangent function, which relates to sine and cosine. This one is just talking about the tangent line. So with geometry, we're just talking specifically about the line that touches the circle once. So notice here on the top, I've drawn a circle with a tangent line there at the top. Tangents, again, by definition, they create a 90-degree angle to the radius that meets the circle at the point of tangency. So what does that mean? Well, if I draw a radius in here, notice I could draw a radius right here. Actually doesn't even touch the line. I could draw a radius right here. Also doesn't touch the line. I could draw a radius right here. Doesn't touch the line. All of these radius pieces don't touch that point of tangency, and even if I tried to make it look like it did, it doesn't really touch the line. However, if we draw a line from the center to the point of tangency, we'll pretend that's straight, that right there would create a 90-degree angle. Okay, now notice the examples down below, they're going to extend from the center out to touch the line of tangency, and or the tangent line, which creates a nice little right triangle. It's very tempting to put the right angle in here because we just think that the hypotenuse is on the top or whatever in a triangle. But remember, the right angle meets the radius, and the tangent line where they meet is the right angle. So looking down here, we're going to look at a few of these examples and talk about their properties. So on this first one, it says label the right angle in the triangle ABC. So again, just like we talked about, the right angle is not here at the center, right? That's not a right angle. It's where the point of tangency meets that radius. So the radius of this circle would be 5, and this right here would be the right angle in this nice little triangle that's built here. Now, it asks us which segment represents the hypotenuse. This is really important so that when we use the Pythagorean theorem, we're setting it up correctly. So notice this segment right here, if this is the right angle, the hypotenuse is always opposite that. So this segment right here, A to C, that is the hypotenuse of the triangle. Then it says calculate the length of the hypotenuse. Now, based off of this radius, since this is a radius, and actually A to D, this little piece right here, that's also a radius. I know that that's 5, but it doesn't really help me because I don't know what this little piece is right here. So what we want to do is look at this as a whole triangle. We're going to go back a little bit. This whole triangle, right, has 2 legs and a hypotenuse. So I know that legs squared, using the Pythagorean theorem, plus legs squared is equal to the hypotenuse squared. And we went over that over and over and over last chapter. So I'm going to say 5 squared plus 8 squared is equal to h squared. Right? Now it's just a matter of solving this. So 5 squared is 25. 8 squared is 64. Right? This is equal to, we called this h squared. And then we add those together and we end up getting 89 is equal to h squared. So I would know that h is equal to, we square root both sides, the square root of 89. Now I could write that as a decimal as well, but the length of that hypotenuse would be the square root of 89. Okay. Again, I'm going to do this one more time, just looking off to the right, one more example. If we're looking at this one, we can say that this guy right here is the right angle. So again, it's at that point of tangency. It says which line segment represents the tangent line. So remember, the tangent line is the one just touching the circle. So it looks like we're going from B to A. Right, so if I were to show that from B to A, this guy right here is the one that's just touching the circle. That's the tangent line. This one's going inside the circle, so it's not that guy. Then it asks us to look at which line represents the hypotenuse. Again, it's important you identify that so that you set your Pythagorean theorem up correctly. So again, we're going to go leg squared. In this case, x is one of the legs. 15 is the other leg, and that's equal to our 17 squared. Again, you guys could solve this. We just square each of these pieces. 225, 289 is 17 squared. We subtract the 225 to the other side. and we end up with x squared is equal to 64. Because it's squared, we square root both sides, and x would be equal to 8 because the square root of 64 is 8. So we know that this leg over here, or in other words, the radius of the circle, this represents the radius. So it could have also asked us to find the radius length, and we would solve it the same way. Now, jumping down, notice that these examples, the radius is there, and we're given, again, we can identify if this is tangent, then this is the right angle right here. So here's my hypotenuse, and then my two legs along the side. The trick here is that the hypotenuse is not 18 in total, but 18 is this piece right here. And we know that, one, by looking at the picture, but the other is, you'll notice this bottom leg is 24. And the hypotenuse has to be the longest leg of the triangle, or the longest piece, so it can't just be 18, right? If we were looking at this, it's actually r, whatever this piece is, plus 18. So my hypotenuse here could really be represented as r plus 18. So now if I want to use the Pythagorean theorem here, I would need to say leg squared. Notice that one of the legs down here is the 24, so we do 24 squared. The other leg is right here on the left side, that's actually r. So plus r squared is equal to, and then we do the hypotenuse squared. Now again, the hypotenuse, and I'm going to put this in parentheses to make sure that we keep track of our pieces, but that's r plus 18, right? The hypotenuse. And then we need to square that. So again, leg squared plus leg squared equals the hypotenuse squared. From there, we're solving just like we have been. So 24 squared is actually 576 plus r squared is equal to, now remember when this is squared, that means there are two of those binomials. So it's helpful, again, you can't just put this guy inside of here. It doesn't work like that. There's an addition sign in there. We've talked about that many times. R plus 18, there's two of them, and if you put them side by side, it'll help you keep track of those. From there, right, we just FOIL these. So we get r squared. Let me put my equal sign there. R times 18 is 18r. R times 18 is 18r, and then we go 18 times 18, which is 324. On the other side, I still have the same thing, so nothing's changed over there. And then we start to simplify. So you'll notice if I'm trying to move everything to one side, if I subtract this r squared to the other side of the equal sign, it actually cancels there, but notice it also cancels there. So your r squared goes away nicely, and you've got 576 equals, these are like terms, so let's add those together. 18 plus 18 gives us 36r plus, and then we have that 324 on the end there. Now, there's no more r squared, so we don't have to FOIL, quadratic formula, nothing. We just need to get r by itself, so I'm going to subtract the 324 to this side. If you subtract that, you end up with 252, and we still have 36r on this side. Now again, it's being multiplied, so we just divide by 36. R is equal to 7. Okay. And again, that's the radius length. It was asking us to find the radius length. Now the one off to the right, just for the sake of time, I'm going to set it up, and then we would solve through it the same way. Again, you need to identify here is the right angle. That's, again, really important because here's your hypotenuse. So when you set this up, again, you're going to go leg squared. So let's start there. We would go 80 squared plus leg squared. The other leg is r. Then you have your whole hypotenuse here, which is 50 plus this r piece. So again, we go 50 plus r and then squared. And then again, we would multiply that out, making sure that our first step was 80 squared plus r squared equals, and then we would write this out as two pieces. 50 plus r, and then we would begin to FOIL and simplify. And again, you'll notice those same patterns work. Okay, maybe I am going to work this one out. Yeeks. Then this is equal to, if we start to FOIL that, that's 2500 plus 50r plus 50r plus r squared. I just want you to see that the same thing happens with our r squareds. You've got one on this side and you've got one on this side, so they nicely cancel out. That's really convenient because then you've got 6400 is equal to 2500 plus, then we add those two 50r's together, which is 100r. Then we subtract this over, and we end up with 3900 is equal to 100r, divide by 100, and we get 39. So same process over and over again, just the Pythagorean theorem. We just need to combine our knowledge of foiling there. All right, on these last ones, so verify a tangent to the circle using the converse Pythagorean theorem. So remember, sometimes we have a triangle and we don't know if it's a right triangle. Okay, Pythagorean. So what we do is we test it. We take the two short sides and we see if it's equal to c squared. So we use that a lot last chapter as well. So for example, here on this left side, we have this example right here, and it gives us a triangle, and it says, well, this little piece right here is 3, this piece right here is 4, and then notice it says this little piece is 2, but because that is a radius length of 3 right there, we also know that this radius length is also 3. So you basically have a triangle here. I'm going to draw it off to the side. And this one's 3, this one's 4, and then 3 plus 2, this guy's 5. And it wants to know if that is a right triangle. Because if it is, then this line, actually this line DE is tangent. So to verify that, you just need to show that it really does work, the a squared plus b squared. So we would do, again, if this works, this has to be the right angle. So you're going to say 3 squared plus 4 squared should equal 5 squared. Okay. So we do this 9 plus 16, and 5 squared is 25. This does give us 25 is equal to 25. That's true. So then we would say, therefore, triangle ABC is a right triangle. And if you verify that it is a right triangle, you've also verified that DE, so maybe I would say, and DE is tangent to triangle, where did I get ABC? All right, take it back. Not triangle ABC, sorry. It's not even a part of this problem. This is triangle CDE. Oh dear. And then DE is tangent to triangle CDE. Okay, I hope that didn't confuse you, but essentially you just need to take the two pieces, and on the right one example, you would do the same thing, right? This little guy right here would be 5, so that full piece would be 13, and then you would verify that 5 squared plus 12 squared, because if it works, those are your two legs, is equal to 13 squared, and you would continue to solve and show that, and then state your conclusion. Lastly, the external tangent congruence theorem, sorry, looking at one too many things, it basically just says if you have two tangent lines coming together, and this makes sense in case of the triangles, I'll show you, but essentially they're saying that if this piece is tangent, this piece DC right here, and if this piece right here is tangent CB, then those must be the same length. And it would make sense if we were looking at it in terms of triangles, because notice if this creates a right triangle, where this piece right here is the hypotenuse, and this creates a right triangle, well, their radius lengths have to be the same, and their hypotenuse has to be the same, which means that this last side, right, if I call that x, that guy also has to be the same. So if you ever have two tangent lines, tangent segments, and I'm just going to write this real quick, so if you look at that theorem on page 576, tangent segments from a common external point are equivalent. I'm so sorry. That is messy. Okay, so I'll just show you an example down here. Again, if we were looking at this, we would just say, okay, well, it tells us that these both lines are tangent, so we know that this piece must equal this piece, so we would say x squared plus 5 is equal to 21. Now, if that's the case, then we subtract. So this is a lot like the ones we were doing in the last unit with our parallelograms. 21 minus 5 gives me 16. If I square root both sides, x is equal to plus or minus 4.